Okay, we're off to chapter 8 here. Last time I think we finished up chapter 5, which was the last chapter that will be on our upcoming exam, which I believe is a week from today or Wednesday. One of those, I think it's Wednesday, maybe coming up next week, I think, if I'm not mistaken. I almost want to say Monday, but I'll double check. So this is going to be chapter 8, which will obviously be exam 3 material here from this point. So in chapter 8, we're going to talk about chemical composition. We're going to talk about really atomic mass, molar mass, Avogadro's number. We'll also talk about calculating molecular and empirical type formulas. So let us get into it. So first off, we're going to talk about atomic mass. And the atomic mass is really the other number that we see on the periodic table there. So when we do look underneath the element, the number that we see there is the atomic mass. And there's a couple different ways we sometimes will use that unit. Sort of traditionally, the use of that unit or those numbers is for the atomic mass, which basically we could say there's 1.008 AMU in an atom of hydrogen. AMU is a atomic mass unit. It's a unit, obviously, of atomic mass. Truthfully, in most calculations that we do, we really don't use those sort of units. We use, as we'll talk about a little bit later on in this chapter, sort of a more convenient unit, which is molar mass, which is grams per mole. The good thing about it, sort of atomic mass and molar mass, is they are numerically the same. So this would, as we will see later on, be the same for hydrogen, 1.008 grams per mole. So we usually will use that as sort of the units. But occasionally AMU per atom is sort of used, and usually whenever we take sort of the numbers off the periodic table there below the symbol, it usually is about 4 significant figures as to how many numbers you should take. Depending on your periodic table, there may be more, but there may be less. Now, obviously, the atom's mass is related to the protons, electrons, and neutrons that there are in an atom, but it's really small, so you can't really take one and kind of put it on a balance or anything like that to weigh it. Chemistry where there is no way necessarily to measure something, a lot of times what they do is they pick some type of standard to compare everybody to. And for atomic mass, it was an isotope of carbon. It was the carbon-12 isotope that they used for the standard here to basically compare the atomic masses of everybody. Carbon-12 isotope had a mass of exactly 12 AMU and had 6 protons and 6 neutrons and exactly a mass of 12 AMU. Again, atomic mass unit is sort of a unit used for that, is also sometimes referred to as a Dalton. 1 AMU is equal to the mass of 1/12 of the carbon-12 sort of isotope. So what they did, they sort of did experiments to look at sort of atoms, and is only about 8.4% as big as, say, the carbon-12 isotope. So basically what they did is sort of a kind of simple sort of calculation to figure out the atomic mass. They basically took 8.4%, which is this guy, right, converted into a decimal, right? Move it 2 places to the right or divide by 100, whichever way you want to do that. So they take basically 8.4% of the atomic mass of carbon-12, and you get something like 1.008 AMU as the atomic mass of hydrogen. Similar calculations were obviously done for everybody that you see on the periodic table. And again, you can take those numbers off the periodic table as, for example, for iron, 55.85 AMU per atom as sort of the units. Now, if you look, though, at carbon, for example, on the periodic table, we actually don't see it listed as 12 or 12 exactly, which you might expect it to be since they chose the carbon-12 isotope as the standard. And when we look at something like carbon and a lot of the sort of elements that we see on the periodic table, really what we're looking at is what's referred to as the average atomic masses. And they're the average atomic masses for all the naturally occurring isotopes for that particular element. So for example, carbon, there's carbon-12 isotope and the carbon-13 isotope. One occurs about 99% of the time, one occurs about 1% of the time. So the number that we actually see on the periodic table for most elements are an average value of all the naturally occurring isotopes for that particular element. Remember that isotopes, right, are the same element, but they have different numbers of neutrons, right, which gives them different masses and different mass numbers, for example, as well. So we can actually calculate the atomic mass like we see on the periodic table there through a certain formula, which is, if you want to calculate the atomic mass, you take the percentage of the first isotope times it by the atomic mass of the first isotope. Obviously, you would convert your percentage into a decimal. You then would actually add it. So sometimes people want to always multiply this part, but you're actually going to add it to the percentage of the second isotope times the atomic mass of the second isotope. Then you would add it and sort of continue that pattern. So if there's a third isotope or a fourth isotope, you basically just continue that pattern or percentage times the atomic mass of each isotope. What is the percentage? The percentage is sometimes called the percent abundance or relative abundance. It basically is the percentage at which that isotope occurs sort of naturally, right? So how do I know if I have all my naturally occurring isotopes? All my naturally occurring isotopes should add up to 100%, right? So if you're given sort of the percent abundance, relative abundance of a bunch of isotopes, and you add up all the percentages and they don't add up to 100%, then you're clearly missing one of the isotopes there, because it should obviously add up to 100%. So percent of the first isotope times the atomic mass of the first isotope plus percent of the second one times the atomic mass of the second one. And again, you just kind of continue that pattern. So if we look at, for example, carbon, where we do see 12.01 rather than 12 on the nose, if we kind of look at those percentages, what we see is a couple of things. We see that the natural abundance, which is another way to sort of talk about the percent abundance of carbon 12 and carbon 13, are 98.89% for carbon 12 and about 1.1% for carbon 13. The mass of carbon 13, as you can see, has a different mass than the carbon 12 isotope, which is 12. This one is 13.00335. So this is our calculation we were just talking about. This is 98%, basically 98.89% converted into a decimal. This is the atomic mass of our first isotope, which is the carbon 12 isotope. This is basically 1.11% converted into a decimal. That is the atomic mass of our second isotope. And as you can see there, we do get 12.01 when we do that calculation, which is exactly what we do see on the periodic table for the atomic mass of carbon. It is important to know that you would never really find a carbon atom that has a mass of 12.01. You would either find one that's the carbon 12 isotope that has a mass of 12, or the one that's a carbon 13 isotope that has a mass of 13 and change. But again, we do typically use these values as the atomic mass. Also, most people don't really call it. Usually average atomic mass is referred to as the atomic mass, but it is, again, made up of all the naturally occurring isotopes. Any questions on that there? So why don't you try one here? What is the atomic mass of bromine? If bromine 79 is 50.7%, and bromine 81 is 49.32%. So take a minute or two to see what you come up with. Okay, so let's take a look here. So if we're going to calculate the atomic mass, we basically have our isotope and its atomic mass for that isotope, and we have the percentage for our second isotope and for that particular one as well. So our atomic mass here would be our first isotope, which we're going to convert into a decimal. So you can move the decimal 2 places to the left, or you can divide it by 100, whichever way you like to do it, times 7992 AMU, plus our percentage of our second isotope there, which we can, again, move the decimal, or if you want, you could divide it by 100. Both works. Does the same thing. And we could times it by 8092. And we will end up with 0.5070 based on these numbers here. About 8043 as our atomic mass based on these here. Any questions on up there? So again, some variations would be perhaps maybe you are given the atomic mass of the element, and maybe you're looking for the percentage of one of them, or you're not given the percentage of an isotope. So you can, again, always assume 100%. So if they only give you a percentage of one, you can subtract from 100 and get the other guy. And there could be 3 or as well. Any questions on that there? So atoms are obviously very small masses, so that AMU in terms of relationship to grams is equal to 1.66 times 10 to the minus 24 grams, which is a very small number. So the average atomic mass for each element is weighted based on the isotopes that naturally occur. That's what we just talked about. So we can, again, use sort of the atomic mass from the periodic table to do some conversions. For example, if we were looking for the mass of one carbon atom, 431 atoms of carbon, and we wanted AMU, we could use basically the atomic mass as a conversion factor. We could say that there are 12.01 AMU in an atom, or we could flip it around and use it the other way, doing dimensional analysis, 12.01 AMU in an atom on top. So in this case, we would start with our 431 carbon atoms, using really the atomic mass as a conversion factor. Our atoms will cancel, and we will end up with 5176 AMU for the mass of our 431 atoms of carbon. Again, we could also look at the mass in AMU of 75 aluminum. Once again, if we go to the periodic table and we find aluminum, underneath it, it will say 2698. Again, and here we're starting with atoms, so we'll use atoms on the bottom so that they cancel, and that ends up giving us 2024 AMU as our atomic mass there of aluminum. Any questions on those calculations? Now, like I said before, you probably are not going to use AMU very much in terms of units. Like I said, we will use more of molar mass, which uses units of grams per mole, which is, again, more convenient sort of unit since we measure things out in grams and stuff like that. So it's really a more sort of convenient unit for us to use rather than AMU per atom. But again, you can use it if you're asked to calculate something in AMU. So let's talk about really the more sort of useful way that we use these numbers off the periodic table, which is molar mass and Avogadro's number. So the molar mass, as we will talk about, basically has units of grams per mole. And Avogadro's number is a number that represents really how many moles, how much there are in a mole of something. So let's start off by talking about really the mole. The mole, which is not the furry guy or anything like that, but it is a name that really describes how much that we have of an object. So for example, if we say we have a pair of something, that represents really 2. If we say, hey, we have a dozen of something, that represents 12. And if you're counting pencils, I think that's what they used to use that for, maybe paper. You got like a gross of pencils is like 144. So in chemistry, we have the mole, which is the unit that represents a certain amount of something. And one important thing about the mole is this abbreviation. So they had to abbreviate it somehow, so they got rid of the E. So it's really important, though, that when you do see MOL, you understand that it represents mole. It does not represent molecules, which is a very common mistake that people make when they see that. They think like molecules. So that is the abbreviation for a mole. And a mole really, just like a pair of shoes or a pair of whatever it may be, it represents a mole does represent a certain amount of something. And that certain amount of something is Avogadro's number. So 1 mole of anything will equal 6.022 times 10 to the 23. So when we use this as sort of an equality, 1 mole equals 6.022 times 10 to the 23. This is Avogadro's number. Now, it is the units that does change. In certain cases, it may be atoms we are using. In some cases, it may be molecules. It may be, pizzas, maybe, and shoes, could be particles, whatever it may be. Probably mostly in chemistry, atoms and molecules are probably the two that you're going to come across the most. So it's kind of the same idea if you say, hey, I have a dozen donuts, right? Or I have, a dozen bagels, or, I have a dozen cards, whatever it may be. They all represent 12, but they are different things. So kind of same thing here. When we say a mole, it equals 6.022 times 10 to 23. And again, really the two common units that we'll use really is atoms and molecules in this case. We use this really as a conversion factor to go from basically moles to atoms or molecules and back. And basically you could go, there are 6.022 times 10 to the 23 atoms over a mole, or you could use it as a conversion factor where moles up on top, 6.022 times 10 to the 23 atoms or molecules on the bottom. It is important, obviously, to make sure that you use your exponent button when you're using Avogadro's number on your calculator so that you do punch it in correctly. Now, it is also important to know that you should not use Avogadro's number in like every calculation. So sometimes people go like, I learned this number, I'll just lay it up in every calculation. And you don't need to do that. You should only be using Avogadro's number if somewhere in the problem, they give you a number that's in atoms, molecules, particles, or they ask you to solve for something that is atoms, molecules, or particles. If they really don't mention any of those words, then you really shouldn't be using Avogadro's number. But definitely if those words are in there somewhere along the way, you probably will use Avogadro's number. Any questions on that? Now, as I mentioned, we could really pull from the periodic table or anybody from the periodic table. We could say, for example, in 1 mole of hydrogen, 22 times 10 to the 23 atoms of hydrogen, which again could give us 2 conversion factors, 1 mole and over 6 to 20 of hydrogen, are 6.022 times 10 to the 23 atoms of hydrogen over 1 mole of hydrogen. We could also do for things that are compounds or molecules or whatever it may be. We could do something like water. If I had 1 mole of water, it would equal 6.022 times 10 to the 23 molecules of water. So here, because water is a molecule, we use the units of molecules associated with Avogadro's number. But again, the number doesn't change. So again, kind of like the dozen donuts versus the dozen bagels, there's still 12 of each, right? In terms of the number, they're just different sort of things. And we also could write 2 conversion factors. 1 mole of water would give you 6.022 0.022 times 10 to the 23 molecules. And again, you could do it the opposite way, 6.022 times 10 to the 23 molecules gives you 1 mole of water. Any questions on that there? Now, another probably more important sort of conversion factor that we use, that we do get sort of from the periodic table, which is related to the atomic mass, is known as the molar mass. And the molar mass has units of, as I mentioned before, 2 units, grams per mole. And whenever you calculate the molar mass of a particular substance, the number always stays with the grams, and it's always based off of 1 mole. So the mole part should always be 1, and the number should always stay with the grams part of it. The molar mass is really taken from the periodic table as well. So for example, our hydrogen there that we saw earlier, that we could use in an atomic mass sort of situation as 1.008 AMU per atom. We could pull it off as the molar mass in a more sort of convenient unit, and we could say that there are 1.008 grams of hydrogen and 1 mole of hydrogen, or the molar mass of hydrogen is 1.008 grams per mole. We could also use this as a conversion factor, where you could turn the molar mass 1.008 grams per mole, or a mole of hydrogen is 1.008 grams. Allows you to do a little dimensional analysis sort of approach here. We also could calculate the molar mass of compounds as well. So if we had water, like our example a second ago, all we would do is basically add up all the parts from the periodic table. So from the periodic table, hydrogen is 1.008 grams per mole, and there's 2 of them, plus oxygen, which is 16 grams per mole. So again, that is oxygen and that is hydrogen there. And basically we just add up all the parts there, and that gives us a molar mass for water of 18.02 grams per mole. Once again, you can turn this into 2 conversion factors. 18.02 grams per mole is 18.02 grams. So molar mass is a really important sort of conversion factor for us. It is the one that allows us to go from grams to moles and moles to grams, which is pretty much what you do in a lot of calculations in chemistry. So molar mass is the thing. As I mentioned before, numerically speaking, it is molar mass and atomic mass and AMU are basically the same number. So that's how we get the same number. You could do the conversion, but it comes out basically the same, involving Avogadro's number and grams to the -24. So actually what we do see on there, a lot of times is referred to also as the molar mass from the periodic table. Once again, much like atomic mass, we do pull it off 4 significant figures is typically what we do take for that. The relationship between Avogadro's number and molar mass is this. You could tie them all together. 1 mole of hydrogen would equal 6.022 times 10 to the 23 atoms of hydrogen, which would equal 1.008 grams. And you could do the same thing for the water. 1 mole of water would equal 6.022 times 10 to the 23 molecules of water, which would equal 18.02 grams. So they are all related to each other like that. Typically speaking, if you need to go from like grams to atoms or molecules, you go grams using the molar mass to moles, moles to atoms using Avogadro's number. Or vice versa, if you're starting with molecules or atoms, you need to get back to grams. You go from atoms to moles using Avogadro's number, and then from moles to grams using the molar mass. Any questions on that there? By the way, the last thing about this is just the relationship between grams and AMU and molar mass, so don't worry too much about that. when you are asked to calculate those are relationships that we saw earlier. When you're asked to actually calculate the molar mass for a compound, it should always be done based on just the formula by itself. So what I mean by that, later on, we will have obviously equations where perhaps, in an equation, we have a 2 in front of the water or something like that, So even if there's say a 2 in front of the water equation, when you're going to calculate the molar mass, it is based just. So you do not want to do that. So sometimes people see it like in an equation, they need the molar mass for a calculation. They go, well, the coefficient is 2 or 3. So they incorporate that into the molar mass calculation. You should never do it. So you should simply just take the formula and add up all the parts from the periodic table just for one of the formulas. And that would be the correct way to get molar mass. Any questions on that there? All right. So why don't we try one here. How many moles of helium are there in 5.46 grams of helium? From the periodic table, if we look up helium, we will see 4.003 listed. So give it a go, see what you come up with. So let's take a look at this. First off, we have grams and we want to go to moles. So do we need Avogadro's number here? The answer is we do not. There's no mention of molecules. There's no mention of atoms. So we don't need Avogadro's number. This again is a grams to mole situation, which is the molar mass. And that molar mass comes from the periodic table, basically. So once we go to the periodic table, we once again could get basically 2 conversion factors for helium in this case, which would be 4.003 grams per mole of helium. Once again, the number stays with the grams. Or we could say that in a mole of helium, there is 4.003 grams. So in this case, we're starting with grams of helium, so 5.46 grams of helium. Doing dimensional analysis, opposites cancel, so grams are on top, so we really are dividing by the molar mass here. So we want to put the grams on the bottom. And here the grams would cancel out. And as was the question, in this case, you would look at the 5.46, and we do end up with, looks like a 1.36 moles of helium. Any questions on that one there? Yeah. Yeah, so when you calculate the molar mass, which is what we just did here, is always 1 mole. So the number always goes with it. And that's what I was talking about earlier. So, if you have like a formula or any of these things, and there happens in an equation be like a number in front, that number represents really how many moles there are. So that would be like 2 moles. But when you calculate the molar mass, it's always per mole, which means you basically just do it off of the formula. So regardless if there happens to be a number in front of it or anything like that, and the molar mass is always basically 1 mole, and the number stays with the grams part always. Yeah. No matter what element it is, when you take the periodic table, that's basically how many grams there are per 1 mole. And if you have to add them together like we did with water, it's basically still how many. Other questions? Okay. So I'm going to try another one here. I'll do that. Let's try, what is the mass in grams of 1 gold atom, which I think is what it says there. So why don't you give that a go? Gold on the periodic table, 197, we'll call it. All right, so see what you come up with. Let's take a look since we're getting to the end here. So in this case, we're starting with atoms, and we do want to go to grams. So I do need to use Avogadro's number here. I know that because I do have atoms, so I definitely got to use Avogadro's number somewhere along the way in my calculation. But I do need to get to grams. So if we think about sort of our pathway here, we could use Avogadro's number to get to moles. And once we have moles, we then could use the other important conversion, which is molar mass, to get us from moles to grams. So that's sort of our pathway to kind of get us to grams. So we'll do the first one first here. 1 gold atom. Once again, there are 6.022 times 10 to the 23 atoms per mole of gold. So we're going to use that as a conversion factor. So opposites cancel, atoms are up on top. So Avogadro's number here will actually go on the bottom so that it properly cancels out. And if I stop point, the atoms cancel and I am in moles. So I'm close to what I need, but I do need to go one more step, and that's going to be the molar mass. I could get the molar mass from the periodic table here, and that would tell me that there is 197 grams per mole. So once again, the 197 is how many grams there are, and 1 mole of gold. Once again, we can use that as a conversion factor as well. 197 grams over a mole, or a mole is 197 grams. In this case, if we continue on with our calculation, we have moles up on top, which means to cancel them, they need to go opposite. That would put our moles of gold on the bottom, our 197 grams up on top. The moles will cancel. Now we are left with grams, which is what we're looking for. We're going to multiply everything across the top, which basically is 197. We're going to come back and divide by Avogadro's number using our exponent button. And we do end up with 3.271 times 10 to the minus 22 grams of gold, which is a pretty small number there for one single gold atom. Any questions on that calculation? So once again, these are two very common sort of conversions we use. And I won't say a lot, but occasionally here, Avogadro's number, but definitely molar mass we do use a lot. So molar mass, once again, from the periodic table. And Avogadro's number is just a number that is sort of a constant that you can remember is this guy. Any questions on that? Yes, sir.
Avogadro's constant, due to the fact that it doesn't.
We'll call it Avogadro's number mistakenly.
It's actually